Yeah. Welcome everyone to the Shannon channel. I'm really happy to have Victoria Kostina from, I was going to say Princeton, but from Caltech.
From Princeton originally, you can say.
Yeah, yeah. And I'm really happy that she's here and she's going to give us a talk. The title of the talk is Towards a Theory of Information for Dynamical Systems.
Thanks very much, Salim. I'm really happy to present at Shannon channel. And hi, everyone. And please, if you have any questions during the talk, don't hesitate to interrupt me. So let's start. Okay, does this work? Everyone sees the slides?
Yeah, perfect, perfect.
Okay, wait, my problem is I cannot see my own pointer. How do I do this so that I can see the pointer? Wow, I cannot point to anything.
We can see your pointer.
Maybe I don't need a pointer. You know what? Maybe okay. I don't need a pointer. So okay, we'll start. So I'm going to start. Today I'm going to talk about the first steps towards a theory of information for dynamical systems. And the motivation for this research lies in the philosophy of Internet of Things, where we have many devices connected over wireless links that can be unreliable, that can be rate constrained, and we would like to communicate to these devices, and we would like to communicate with a goal in mind. So rather than, as in Shannon, classical Shannon information theory, where the goal of communication is to transmit a message from one point to another point in time or space, here the goal of communication is going to be to achieve a certain control goal, right? So for example, what you see in this example is a remote surgery, telesurgery application where a robot is performing a surgery on a patient and it's being remotely controlled by a surgeon who is 200 kilometers away. So remote control is an application of this theory. And this is another application where we have multiple devices that can interact with themselves, among themselves and with the environment, and share information among each other, and in order to achieve some goal again. Right? So the communication here happens not for the purpose of delivering a message, but in order to achieve a goal. Okay, and this is another motivation for this theory, and that is that we can gain insights into the biological processes in the human body using the tools of control theory and information theory. So actually, molecular control processes can be modeled using linear stochastic control theory, and we can use information theory to quantify, again, the amount of information exchanges that is needed in order to do something in molecular communication. But our goal here is going to be to study information-theoretic trade-offs for this system. So for these systems. So here, this is what we have in mind. We would like to characterize a curve which shows the cost. So this cost is related to the goal of what we would like to achieve. So the cost versus the channel quality. So what is the quality of channel, which is the number of bits, let's say, per second that this channel can reliably transmit, that is required in order to achieve a certain control cost. And we are interested in the entire trade-off, this channel quality versus cost. And then we might be also interested in the asymptotes, and these two asymptotes that you see here, the vertical asymptote and the which is the minimal cost for perfect channel. So this is the under the purview of control theory. So control theory really knows very well how to understand that. And then the other asymptote, the horizontal asymptote here, this is the minimal channel quality for stability. And stability means any bounded cost. So to achieve any bounded control cost, what this asymptote shows is that you need at least that a channel that can send at least that many number of bits per channel use. Okay, so we would like to characterize, this is the goal, we would like to characterize information theoretically these fundamental trade-offs between the cost and the rate that we need to achieve that cost. And it's a difficult problem in control. And why? Because information theoretic tools at the first glance, don't seem to be very well suited for problems that involve feedback and very low delay, which are present in control problems. And here I outlined the challenges. So a typical information theory problem contains sources or channels that are stationary and memoryless. And the way we code for these stationary memoryless sources or channels, we do block compression or coding for channel noise. So data processing proceeds on block by block basis, right? So so we take a block of data bits of length k, and we map it to a block of length n, and then we transmit this over the channel. And the important part here is that we forget about the past. Both the encoder and decoder forget about what happened in the previous blocks. Whereas communication for control really requires infinite memory at the encoder and decoder about the past. Why? Because in systems, let's say the location of the system is highly at time I is highly correlated with its location at time I minus 1, and therefore it doesn't make sense to throw away everything that we collected, all the information that we collected previously. So we really do need to rely on memory. And that means using convolutional coding rather than block coding. And delays, right? So delays in classical information theory, delays can be tolerable, whereas in communication for control, delays are really catastrophic. So if we wait until we can code over large blocks of data symbols, then your drone or your system can spiral out of control. So it's really of paramount importance to be able to code with zero delay. And so the final challenge here is that in a typical information theory problem, the data is static. So this is something that's given to the encoder. It doesn't change. The encoder cannot change the data. Whereas in communication for control, the encoder can actually modify the data, the future data that it will need to encode at the next step. Right? So we somehow need to be able to account for that fact that the encoder, whatever the encoder does, it affects the data that it can see at the next step. And this is a well-researched area. So here I mentioned some of the relevant works, but still there is a lot that is not understood. And we're going to focus on 3 simple problems. So the first one is going to be remote control over a rate-limited channel. So here we have a system which evolves according to the equation that you see. So xi, this is the state of the system at time I. And here let's just think that this is a scalar, real number. And then vi, this is the random noise, the random disturbance. And we're going to assume these are id. And the ui, this is the control action produced by the controller. And the goal here is to bring the system to as close to zero as possible. Right? So our cost, control cost here is the mean square error. We would like to minimize the total accumulated mean square error cost over the time horizon t. And what we can optimize in order to achieve this minimal mean square error cost is we can optimize the encoder and the controller. So what's shaded is given to us, the system and the channel are given to us, and we would like to optimize the encoder and the controller. And what does it mean to optimize these two boxes? Well, it means to choose the encoding sequence and the control sequence so as this mean square error cost is minimized. Okay, and here you can see that how the controller, how the encoder can affect what happens at the next step, right? Because whatever it produces at step I is going to be used by the controller to produce this UI, which is then going to be affecting the next step of the system at time I+1, which the encoder will need to compress next. Okay, and the next setting we're going to look at is remote control with side information. So here everything is almost the same, except that the controller has access to this additional observation about the system, which is a noisy observation. So think of this a control scenario where I'm trying to control a flying drone, and I have some maybe visual information. I'm the controller, which represents noisy information about the true system state of this drone, which can be, a vector state containing the three location coordinates, the velocity coordinates, the acceleration coordinates, and so forth. Okay, and then the third scenario we're going to look at is remote control over a rate-limited channel with multiple noisy observers. So here you have several sensors. Well, I only drew two, which measure the system state independently, and what they see is a noisy version of the system state. And so, there are possibly multiple encoders that observe those independent noisy observations, and they want to compress those observations so as the single controller can reliably control this system. Our goals are the following. So we would like to identify information-theoretic quantities that are relevant to the fundamental limits of these causal coding problems. We would like to also be able to evaluate those quantities. So we're really looking for information-theoretic quantities that are computable. And we would like to show coding theorems linking those quantities to their operational meaning. And we would also like to take all these information-theoretic insights and propose coding strategies and maybe design strategies even for these control systems that can approach the fundamental trade-offs that we're going to determine between rate and cost. Okay, so a very important result that we're going to be relying on is a separation between control and communication. So it turns out that as long as past controls are available at the encoder, then control communication separation holds. And what it means is that the total cost in controlling a system separates into two terms. So the first term here is control cost, assuming that the controller observes xi. And the second term here is the distortion in tracking xi, in causal rate constraint tracking of the information source. So the nice thing about this is that the first term here is very well understood by control theorists. So here, the controller has direct access to system state. And so there is no rate constraints involved. And this is a classical problem in stochastic linear control, which people have a very good understanding about. And then the second term here, this is the information-theoretic term. So this is distortion in tracking this system state. And of course, this only holds assuming that past controls are available at the encoder. So this is an important assumption throughout the talk, which ensures that this separation holds and which ensures that we actually do not need to worry about the encoder affecting the future state of the system. And what does it mean operationally? So let's just go back for a second to our first setting. So what does it mean that the encoder has access to past controls? Well, think of it this way. Think of the system and the encoder being co-located, which means that the encoder can see everything the controller sends, right? And so this also makes sense to have this rate constraint on this downward link from the encoder, which is co-located with the system. Therefore, it sees this UI directly, and then it needs to transmit to the controller via this rate constraint channel. Okay, and then in other scenarios where this is not ensured, like if the encoder is not co-located with the system, say, then what this separation result hits at is that if we have design freedom in designing control systems, in many cases, it actually makes sense to implement this highly reliable feedback link from the controller to the encoder. If it's not, provided that it's not already there due to the operational scenario, like in this scenario where encoder is co-located with the system. Okay. So what does it mean for us? Well, it means we can greatly simplify the system. We can basically only focus on understanding the second term. Okay, so we can reduce all our problems to tracking problems. So remote control over a rate-limited channel becomes point-to-point causal tracking. Remote control over a channel with side information becomes causal tracking with side information. And control with multiple noisy observers becomes causal tracking with multiple noisy observers, subject to mean square error cost. And the important observation here also is that notice that in this equation for system state that we have here, there is no longer UI. So this is uncontrolled system state. And the reason we can do this, the reason we can throw out UI is because everyone knows past UIs. So this is side information available to everyone. So we can eliminate it from the tracking problem. Okay, so we reduced all these problems to problems of tracking.
Victoria, I have a question.
Yes.
I have explained.
Yes.
Yeah, so what do you mean exactly by the tracking problem?
Oh, I'm going to introduce it in the next slide.
Okay.
Yes. So we would like to, we would like to have a representation of this system xi subject to this mean square error cost that you have here. So rate constraint representation, zero delay representation, such that it's actually mean square error cost is okay. There is a typo here. I apologize. So let's see the next. Let's see what causal tracking is. So this is the setting. So we're observing x1 to xt. So we are looking at the system over a time horizon, and at each time I, the encoder produces a bit string, so it quantizes, produces a quantized representation, and two important things about this. So this is zero delay. So the encoded bit string at time I has to be produced at time I. And another very important thing here is that the encoder or encoders, in those cases where we have multiple encoders, have memory of the past. So when you are at time I, you remember what happened at previous times. Both the encoder and the decoder remember that. Okay, and what we would like to do, sorry, let me show you the first here. So the design, so this is the causal tracking problem, right? So we would like to track the source. So the decoder produces a representation of xi, and the goal here is to design the encoder and the decoder to minimize the total mean square error cost over this time horizon, right? So we have encoder and decoder that has zero delay. So whatever they produce, so fi is produced at time I, gi is produced at time I, and xi hat is produced at time I. So they cannot wait. Neither the encoder nor the decoder can wait before they form this their outputs. And the goal of all this is to minimize the total mean square error cost that you see here at the bottom of the slide.
So Victoria, so is this related to, or what is the relation to rate distortion theory? Is it similar, or there's?
Yeah, it's a causal rate distortion function. This is what which represents the fundamental limits of this problem. So this is exactly where I want to get at with this talk.
And T here is time, or the number of encoders?
So what is, sorry?
And the goal, there's T, the parameter T. What is?
So T is the time horizon. So
time. Okay.
T is the time horizon.
Okay.
So please don't confuse it with block length. It's not block length that we code over. This is just time horizon, so that we are observing our system over. So here we are observing our system over the time horizon of length T. Okay. And this mean square error, long-term average mean square error is evaluated as like total accumulated mean square error over this time horizon.
Okay.
Okay. So and let's look at the source now. So the xi source that we're going to be focusing on. So this source is known as the Gauss-Markov Source, and it's a very simple model for understanding sources with memory. Okay, so here, VIs are these disturbances, additive disturbances, and A, this is the system parameter, which says a lot about this source, actually. So if the absolute value of this parameter is less than 1, then what we have is an asymptotically stationary source, meaning that if you observe the Gauss-Markov source over a very long time horizon T, then it will settle down the variances of xi's in the limit of large I are going to settle down to a to a finite stationary variance. And so this is the nice case when the source is stationary. And if A is 0, then you have your normal ID Gaussian source. And if the absolute value of A is greater than or equal to 1, then what we have is a non-stationary source, which means that in the limit of large I, it blows up, like the variances of this axis. So X could be anywhere, basically. And this is the reason why memory is so important in order to be able to track these sources that are non-stationary. Okay, a particular case is A equal 1. So this is a source that is non-stationary, and it has a name. This is the Wiener process. Okay, so this is the model, a very simple model for understanding sources with memory. And then there are various generalizations. So you can look at vector version of this, for example, where Vi becomes a vector, Xi becomes a vector, and A becomes a matrix. Okay, so the way I'm gonna do this talk, I'm gonna talk about all these 3 operational scenarios I introduced in the beginning, but the most of my time is going to be spent on the most basic one, point-to-point, causal tracking. And then I'm just gonna say a few words about the other 2 scenarios where we have side information, where we have multiple encoders, just to illustrate the point that the tools that we're going to be using here are not limited to this point-to-point scenario, that they can be extended to understand the other important operational scenarios that involve multiple encoders, for example. Okay, so this is a theory that can be extended beyond point-to-point. Okay, so this is the point-to-point causal tracking problem. And let's look at it. So what the point I want to make is that it's important here that we are observing this system over multiple time instances, over the time horizon t. So if we look at what happens at each step I, okay, this is what happens at each step I. The encoder observes xi, and it has side information that contains all the past decoder outputs. And this is the side information that is also available to the decoder. So this side information represents the memory of the past. Right? Because to code for these sources with memory, we really do need to have memory of the past. And what you can see here, so if we just focus at step I and try to understand this problem just looking at step I, what happens here is that this side information available to both encoder and decoder is a function of what we did at previous steps. Right? So if we were to optimize the encoder and decoder at only looking at step I, we really cannot do this because this side, we don't know what this side information is. Right? It depends on what we did previously. So looking just at time I, we cannot optimize this problem. We really need to somehow look at the joint optimization of this entire encoding and decoding sequence. Okay, and the way we do this is look at this over this time horizon t and ask this question, like what is the sequence of encoding and decoding functions that achieves the minimum MSE over this time horizon, and what is the minimum number of bits that is comparable with that MSE. And when we look into problems over a time horizon, what comes into play is causal conditioning, which is a very useful concept for systems with feedback. And this concept was introduced by Gerhard Kramer in 1998. And so what you see here, the first formula here, this is causally conditioned kernel. And so given any joint distribution between two vectors, f and g, you can always form this causally conditioned transitional probability kernel. And then a very important observation here is that any joint distribution between the vector f and the vector g can be written in two ways. So the first way is the bias rule that you all know. And the second way, this is the one that's going to be very useful for us when we look at these problems with feedback. And any joint distribution can be decomposed in this way, which we can think of causal Bayes rule. And then there is a pictorial representation. And so you can think of this two links, right? So the forward link from f to g, which gives you the causally conditioned kernel of G causally conditioned on F. And then there is this feedback link, which happens with delay 1, that represents how the past of G affects F. Okay, so D here is always going to be denoting delay by 1 in this talk. Directed information introduced by Massey is given by the following formula that you see on top of this slide. But actually, I like more the alternative representation of it written below, which tells us that this is just a divergence, conditional divergence, the relative entropy between this causally conditioned kernel and the unconditional kernel of YT, given the true distribution of XT. Right, so what does it, just one more word about this. So what does it represent, this causal, this directed information? Well, you can think of it this way. So this is the information that flows from F to G in this forward direction. So this would be directed information from F to G. And then in the backward direction, you can look at directed information from the past of G to F. And the total mutual information is actually a sum of these two directed informations. Okay, so now we are ready to introduce a causal rate distortion function, which is defined as the following infimization problem that you see here on the top of this page. And what the form, I'm going to give you a few formulas, and the formulas I'm going to give you are going to be for the scenario of large time horizon. But actually, there is no, the only reason for this is that in those cases, we can eliminate those boundary effects of what happens at the boundary, and simplify those formulas. But the theory really applies for finite time horizon as well. I mean, as finite as t equal 2. But formulas simplify as we take this time horizon to infinity. Okay, so we introduce this function, and the important point to make here is that we will actually see that this function has an operational meaning. So this is what describes the fundamental information-theoretic limits of causal tracking. So, okay, so the next question is it computable? Okay, because if you look at this thing, R of B, this is the limit as t goes to infinity of a sequence of these t-dimensional convex optimization problems, right? So this looks pretty complex. So the next question that we should ask is it really a useful quantity? Can we compute it? And it turns out that yes, in some cases, yes. And actually, this computation was done by Gorbanov and Pinsker back in '74, and they did not call it directed. They did not call it directed information. There was no directed information concept in that time, and they did not specify the operational meaning of this. But they computed this limit of like if you look at this paper, this is essentially what they computed. So we can take that result and declare happily that, at least for the Gauss-Markov source, this function is computable. And you see that the formula is very simple. Nice, okay. And if we just look at this formula, then we can gain some insight as to why memory is useful. So if we look at two settings here, so in one setting, we are coding at time I, and we are forgetting everything that happened before. So this is what's labeled causal here on this slide. And, oh no, sorry, this is what's labeled classical. So classically, we would code, you would encode a block of length n, so x could be a block. So you would encode a block of length n, and you would forget the past. So this is labeled classical. And then what's labeled causal, this is the causal setting that I was talking about. And so if a equals 0, which means Gaussian memorial source, then there is no benefit to memory, because if we plug in a equals 0 to Gauss-Markov formula, we notice that the two rate distortion functions are equivalent. And if a is greater than or equal to 1, then what happens is that because this variance of the source, of this non-stationary source, as I goes to infinity, blows up, so that you cannot encode it with any finite rate, with any finite distortion. So without memory, without this memory about the past. So the classical rate distortion is going to blow up, but the causal is going to be finite. And then if a is less than 1, which means that the source is asymptotically stationary, then there is a gap between causal with memory and classical without memory. So it's beneficial to use the memory.
Victoria, I have a question. So
Yes.
Can you remind us the difference between the classical and the causal? I think I can see, but maybe, I just want to clarify.
Right, so the classical saying, yeah, this is a good question. So I wanted to make sure everyone understands. So in the classical setting, what I refer to as classical here is throwing out this side information. X.
At the encoder.
At both encoder and decoder. Both of them throw out side information.
Okay.
Just try to do as best as they can without this memory.
So no feedback, that's what you mean.
So no feedback, yes. Yes.
Okay. Okay.
Okay, so benefits of memory are great. And
how come classical is bigger, the rate? Maybe.
How come classical is bigger? Because we're forgetting the past here, right? We're forgetting the past. We're not using the memory. We're not relying on the system state. The problem here is the following. We are looking at this. Yeah, Gauss-Markov source, you see the formula here. Mm-hmm. So if a is greater than 1, it blows up. So if you forget the past, you cannot really do anything.
Okay.
Right. So you really, yeah, the point of this slide is that we really do need memory when we talk about tracking, zero delay tracking of non-stationary sources, especially. Even for stationary sources, with memory, you still need this memory of the past, but there is a penalty. There is a penalty for not using that memory. Whereas if the source is non-stationary, then the penalty for not using the memory is infinite. Okay. So one of our results is the following bound. Right. So what I was talking about is this function computable? And what Gauss-Markov showed is that, at least for the Gaussian source. So here we showed a lower bound for a wider class of sources where the additive disturbances are IID, but they're not necessarily Gaussian. And the lower bound is given by this formula that you see here. The difference with the Gauss-Markov formula is that the variance of the noise is replaced by its entropy power. And this can be viewed as a causal counterpart of Shannon's lower bound to rate distortion function. And this is what the classical Shannon's lower bound is. So you see the formula here for the classical rate distortion function, which is bounded below by this formula that you see. And an interpretation of this formula is this volume division argument. So what it says is that the effective volume of the space that X occupies is given by the volume of this ball of radius squared of n of X, which is the entropy power of X. And then what the formula shows, Shannon's lower bound, is the number of balls, the log number of balls of radius squared of d that you need to cover this effective volume. So this is the intuition, and it's a classical tool. It's a very nice tool because it serves as a closed form proxy for a distortion function. So as you know, the classical rate distortion function is given by a convex optimization problem, and that problem, in some cases, it has closed form solution, but in many cases it doesn't. And we can compute it using convex optimization solvers, provided that the source alphabet is not too large. But what's nice about Shannon's lower bound is that it gives us a closed form proxy for this fundamental rate distortion trade-off, which allows to simplify the analysis, gives us intuitive interpretations, and so forth. Yeah, and the good thing about this bound is that it's also tight, provided that the distortion is small. So in high definition regime, it's known that this Shannon lower bound is meaningful, meaning that the gap between the true rate distortion function and Shannon lower bound is vanishes as distortion goes to 0. And what we show is that, so we show what you can think of a generalization of this to a particular case for causal coding. So it tells us something about how these balls behave when the encoder and decoder are constrained to be causal. And so the reason we can form these distortion D-balls in non-causal compression is because it's non-causal. So the shape of these balls is different than when they're constrained to be causal. So you can think of this result in this way, that it tells us something about the shape of this, of what the best encoder and decoder produces, or should produce when they're constrained to be causal. Right, so just like this result, which says that the classical Shannon lower bound is tight, what we show is that this causal Shannon lower bound is also tight in some sense. And this is a matching upper bound to the lower bound that I showed in the previous slide, which says that the output entropy of, there is this quantizer whose output entropy is bounded above by this formula that you see. So the first term here, this is this causal Shannon lower bound. And then there are two more terms. So the second one is the high definition term, which vanishes as the target distortion vanishes. And the first term, this is the space filling loss. And this is a constant, even for scalar system, even when xi is scalar. And it also vanishes as if we take the dimension of the system go to infinity.
What do you mean by dimension n? So
yeah, so dimension n. So actually, the setting I was focusing at mostly was where, so dimension is the dimension of this xi's.
Oh, true.
Right. So it can have a spatial dimension n.
Okay. So for example, in the multiple sensors example, so you can have like n sensors. Is that kind of a practical setting where this may arise?
No, I mean your system state. Actually, yes, of course it can arise there, but it can also arise in
your system state
in this point-to-point system where your system state is a vector.
Okay, good.
State. Yeah.
All right, thanks.
Okay. How do we show? So this is an actuability bound. So how do we show this bound? So this is the idea. We actually analyze a classical scheme, differential pulse code modulation, which works as follows. The encoder has a state estimate before transmission. That's so based on all the past. So this is its best prediction about where the state is going to be at the next time, given the past. Okay. And then what it sends the innovation with respect to that prediction. So it quantizes the difference between the true state and this prediction that the decoder also can compute. Right? So the important thing here is that both the encoder and decoder here, because they have access to this past, they can compute this predicted state of the system at time I, given the past predicted value by simply multiplying it by A, since noise is zero mean here. Okay, and then all the encoder sends is a quantized value of innovation, and the decoder forms its estimate by adding that quantized value to its previous to the prediction that it had previously. And so this is a known scheme. So our contribution here is a new analysis for the scheme, actually showing that it's optimal in this sense of this theorem, that it achieves at least at high definition, it approaches the lower bound that we have. And we can plot this. Right, so the red curve here, this is the converse result that we have, the causal Shannon lower bound, and the blue dashed curve, this is the what is uniform innovations DPCM quantizer achieves. So you can see that, and this is for scalar system. So you can see that the gap is this is in knots, so this is less than half knot between the two curves. So the point is that the causal redistortion function and the causal Shannon lower bound in particular really do have operational meaning for these problems, right? Because there is a scheme that approaches it quite closely. Okay, a word of caution here. So what?
I have a question. One more question.
Yes,
based on your comment. So when you said it has an operational meaning because the scheme approaches, but do we know that this is actually the fundamental limit?
For any distortion D, no. So what we know is this. So this is our achievability bound, right? So what it says is if you take D to 0, if you take dimension to infinity, then these two guys are going to match, right?
Okay.
But otherwise, they're going to be close, and how close it's determined by those.
So it's asymptotically, that's what we know.
So it's that's right. So it's yes, that's an asymptotic result both in terms of distortion. So it means low distortion, and in terms of the spatial dimension. You know, even though we can compute it for any n, and this O of one term, it's a small constant, and so you can have a bound, right?
And this is for infinite horizon, right?
This is for infinite horizon, right? But as I said, the finite or infinite is not so important in this problem.
Okay.
But formulas, all these formulas simplify greatly when you take the time horizon to infinity.
Okay.
Okay. Okay, so a word of caution. So the quantizer that we use here actually uses variable length quantization. And what it means is that at each time step, we are transmitting a string which has variable length. And this is how it works. So you see this picture here. And so the blue thing, this is the PDF of what we are encoding. And we quantize, so it's a uniform scalar quantizer. So we quantize, and then we label each quantization bin, starting from the most likely quantization bin to the most likely by lexicographically, by strings that have increasing length as the probability of that the probability of that quantization bin decreases. Okay, so the important thing here is that this satisfies our rate constraint on average, right? So on average, over realizations, you're going to be transmitting that many bits, but some noise realizations rare noise realizations may incur a longer description. Okay, so it's not a hard constraint on the maximum number of bits that we send at each time instance. And a very nice thing about this is that, regardless of where the noise brings us, we can always guarantee is this scheme that we are always able to represent it within the distortion that is given by the width of our quantization bin, like regardless of how rare our noise realization is. And this is actually a very important distinction for these problems in tracking, because imagine we looked at fixed length quantization. So instead of having the soft constraint on average rate, we had a hard constraint. So a simple example for this is 1-bit quantizer. So imagine that at each time, you can only send 1 bit about what you observe. And a very interesting effect that happens here, which highlights the dynamic nature of this problem, is the following. So suppose we have a static quantizer, meaning that we fix this quantization representation points labeled here by plus and minus. Right? So if our noise is positive, then we send the plus. We construct to this value given by the plus, otherwise we send the minus. And suppose that it's a static quantizer, meaning that you cannot move as time passes. You cannot move this chosen in advance representation points. And then what is going to happen is that eventually, with probability 1, if we are looking at this system over an infinite time horizon, then eventually with probability 1, we are going to encounter a noise realization that is going to take us out of what we understand about the system. And it's going to be so large that our distortion is going to be so large that we are not going to be able to catch up with the system afterwards. So everything is going to break at that point. The system, the distortion, our tracking distortion is going to blow up with probability 1, provided that these noise disturbances are unbounded, right? Because with probability 1, regardless of how large, there's probability 1 arbitrarily large noise realization is going to be encountered, which is going to induce this arbitrarily large distortion at that time step. And if we cannot move this reconstruction points, that means we can never recover from that effect, that the system state is going to run away from us. And this is an observation made by Nair and Evans in 2004 paper. So the situation is very different when we look at fixed rate quantization versus variable rate. And in this in this context, we asked this very simple question. So for this scalar Gaussian system, we asked this very simple system: if A is between 1 and 2, can we achieve any bounded mean square error with 1 bit? And so Nair and Evans said that if your quantizer is static, then you cannot do this. You cannot achieve any bounded distortion. But what you need to do, and this is observed by people previously, what you need to do here is you need to have an adaptive quantizer. So a quantizer that zooms out, zooms in, based on how you're doing. So it changes. It's not static, but the encoding and decoding function changes time. And so it's a very simple question that we asked, but for which there was no answer in literature. And so what we did in this paper, we showed a simple scheme showing that, yes, you can control the system with one bit. But what's interesting about, I think, this whole area of fixed length quantization, of fixed length tracking of dynamical systems, is that there's so many open problems. Because even the stability question, so here we didn't even ask what is the the rate cost trade-off. We only asked, can we achieve any bounded cost, right? So even that question was not fully understood before. And the next very natural question to ask is can we approach this lower bound with fixed rate quantization? And simulation results actually suggest that you can. So you can have a quantizer, a Lloyd-Max type quantizer, which you can plot and show that, yes, it is also close to this converse, but there is no proof. So I think that's a very, very interesting open area to understand how fixed rate quantizations can do in this context of the full rate versus cost trade-off. Okay. And this brings me to part 2. And as I said, part 2 and 3 are only going to give you the most basic idea. But there's actually going to be almost no formulas in this. So let's just look at how these tools can be generalized to these other settings. So this setting, causal tracking with side information, the non-causal counterpart of this is Gaussian Wiener-Zipf compression. So pictorially, you can represent it as the top picture here. And a very famous and unexpected result of Wiener-Zipf says that asymptotically, having this side information in the Gaussian case, right? So X and Y here are jointly Gaussian. So having this access to this side information only at the decoder performs as well as having this side information also at the encoder, right? So it's very counterintuitive because it seems like having access to this side information at the encoder should help us. But what Wiener-Zipf showed is that it doesn't help us. For Gaussian case, at least in this asymptotic regime of infinite block lengths, there is no benefit of having access to this side information at the encoder as well. And so what we do here, we generalize this result to the Gaussian tracking setting with side information. So what we show here is that also in tracking of a Gauss-Markov source, where X is Gauss-Markov source and Y is a noise-corrupted version of this source with Gaussian noise. So a very similar effect holds, that having access to this side information also at the encoder is useless. And actually, I'm not even going to show you the formula, just only give you the bottom line. The bottom line is that using this directed information framework, we can get computable rate distortion function for causal tracking with side information. And so we can plot it, we can gain insights into this problem. So here, what is plotted is this causal rate distortion function with side information for tracking of X, which you see here on the right on the upper right corner. X is the Gauss-Markov. Actually, you don't need U here because everyone knows U. Remember, so you can just make U 0. So this tracking of this Gauss-Markov source with this side information yi, which is as you see, this is the noise corrupted version of X. So both W and V are Gaussian ID independent random processes. And what we plotted here, we fixed A, so this is the Wiener process. We fixed the noise of the variance of V to also 1. So this is written in the bottom of the slide. And we plotted the causal rate distortion function for different parameters of the observation process. So we varied the parameters of C and the observation noise W. Okay, and the labels here, so this is sigma square. As you see, the curves are labeled by sigma square, X causally conditioned on Y. So what it means is that what it signifies, this is the asymptotically achievable estimation error in estimating X, the process X given Y, without rate constraints. So so without rate constraints, this problem is well understood. The solution is given by Kalman filter. The best estimate of X given Y is the conditional expectation of Xi at time I is conditional expectation of Xi given all the past of Y. And the Kalman filter gives us a very simple iterative formula and a filter and implementation for this filter of how to compute these conditional expectations. And for various parameters of this observation process, what the filter achieves in the limit of long time horizon is can be computed from that Kalman filter recursion using Riccati equations, and the value for that asymptotically achievable MSE is given by the sigma X conditionally conditioned on Y, causally conditioned on Y. And so the green curve here, this is for the case when this value is infinity, which means there is no side information, so no one has access to Y. And this is exactly the case we looked in the first part of the talk, where there was no side information. And one thing that is interesting to observe here is that this rate distortion function never vanishes. Right? So because this process is a non-stationary, to achieve any bounded distortion, you need to keep sending bits, regardless of how large your distortion is. Right? So this is very different from, let's say, non-classical rate distortion function, where you can, if your target distortion is greater than or equal to the variance of your source, then you don't need to send any bits. Right? And this is exactly what happens when, in this scenario, is with side information, or when the decoder has access to this Y. Right, so when the decoder has access to this Y, the very important effect that happens is that this, for large enough D, the rate distortion function vanishes, and then we can also, using our formulas that are not shown here, but that are plotted here, we can quantify how the shape of these curves. So what's obvious here is that the larger, so the noisier our side information is, the worse this causal rate distortion curve is. Okay, and a few words about causal tracking with multiple noisy observers. So this is actually a causal zero delay version of the Gaussian CEO problem. So in the Gaussian CEO problem, what we have is we have an observation of a Gaussian, k noisy observations of a Gaussian that are observed by k separate encoders, and that encode those observations independently and transmit the information to the common decoder, which is called the CEO, Chief Estimation Officer. who takes all this information and produces the estimate of x. And so this problem, what it is at its core, this is a causal version of that Gaussian CEO problem, and the picture is what you see here. Right? So it's zero delay. You have k encoders. Here again, you have side information. You have access to what happened in the past, and the CEO takes all these rate constraint representations from all of the encoders and produces its estimate of that source x. And it is a very interesting problem even in the classical case, and there are many interesting effects. For example, you can quantify the loss due to separation. So if these encoders could talk to each other, then the rate you can achieve is actually lower. So there is a penalty due to the separation of the encoders, due to the fact that they cannot coordinate, they cannot cooperate. So it's a very different problem from the previous problems we looked at. And I'm just going to give you one formula. So what we did here, we looked at the symmetrical version of this problem, and we studied the achievable sum rate. And so we gave a formula for that. And this case, this gives a special case of that formula in the limit of large number of identical encoders. Right? So think of it this way. So you have very, very large numbers of encoders. So as k goes to infinity, what's interesting here is that the sum rate that you need is still finite. And so the expression here on the right-hand side is still finite, even with infinite number of observers. And what you see here, there are two terms. So the right term, this is actually just a different way to write the causal noiseless rate distortion function. So this is what we would get if we had direct access to x and just one encoder. And then the first term here, this is the penalty due to isolated encoders. And the classical version of this formula was given by Ohama in 98, and so this formula generalizes that insight to the case of causal tracking with multiple isolated encoders. Okay, so the takeaways is that this machinery, I think, is very useful to gain insight into these problems that have feedback, that have memory, that are causal, that are zero delay. So it's a very useful tool because it leads to tractable fundamental limits, which means that tractable means that we can compute them, and fundamental limits means that it has an operational meaning. So directed information has an operational meaning in these problems. And what it also helps us to do is it helps us to gain insight into good coding schemes for tracking and control. Right? So the insights that we saw, for example, is that fixed rate quantization is much more challenging in these problems than variable rate quantization. Having access to good feedback about the past is essential. And if you have variable rate quantization, if you can afford it, then very simple schemes exist, such as classical DPCM, which is actually is very good. As we showed, it performs very close to the fundamental limit given by the directed information. And there are many, many, many open problems here in this area. So thanks everyone for your attention. And I'll take any questions if there are any more questions.
Thanks, Victoria. I don't know if there's any question, maybe they can just ask it. If not, so I want to thank you again, Victoria.
Oh, thank you.
See you soon, maybe.
Thank you very much.